Good morning, chemistry team. Coming at you with video 3 in our chemical reaction, chemical equation journey. We've mentioned this word before, the infamous stoichiometry. We said that when we were looking at the information you can glean or extract from a chemical equation. If I give you it's got to be balanced. If you have a balanced chemical equation in front of you, you see those coefficients, right? Those coefficients represent the mathematical ratio, just like if you're cooking and you've got a recipe, you've got a certain amount of each substance that you have to mix together in those correct proportions to create the correct proportion of the species that you're after. If those proportions are off, you got a problem. All right, so that's all stoichiometry is. It's those mathematical ratios from one species. It could be from one reactant to another. How much of this reactant do you have to mix with this reactant? Or you could go reactant to product. How much of this reactant if I have this much reactant here, how much of that product would I get? I could work it backwards. To get this much product, how much of this reactant would I have to start with? Stoichiometry is possibly one of the most common types of calculations you're going to do in your chemistry lifetime. So it's really important. Really, it just stems down to one thing. What is this mathematical ratio called? It's called the stoichiometric factor. It's that number ratio of this product here to this reactant, or this reactant to this reactant. What are those balanced coefficients, those numbers? The 2's, the 3's, the 5's. Is it a 2 to 3 ratio? Is it a 5 to 3 ratio? A 1 to 1 ratio? That ratio is called the stoichiometric factor. Some people call it the stoichiometric ratio. All I see that as is a conversion factor, just like, centimeters to meters or pounds to grams, anything like that. You have a number that relates those. But in this situation, the conversion factor allows you to go from one species to another species. Like in the combustion reaction we did in the last one, we had, I think it was butane on the left-hand side and reacting with oxygen, giving you carbon dioxide and water. So I could take a certain amount of butane, and knowing that stoichiometric factor between butane and, say, carbon dioxide, I can say, well, if I take 5 grams of butane, how many grams of carbon dioxide would I produce? Knowing that those integers between them allow me to convert from butane units to carbon dioxide units, or I can go from any one species to any other, front, forward, or backwards. It doesn't matter, as long as you know what those balanced coefficients are. Now, what those units are, right, is going to be very particular. So let's take a look at a balanced chemical equation and look at the units we need to use for those numerical integers from the balanced equation. Let me erase this board and get up a balanced equation for you. This is similar to the butane combustion we did in the last video, but this one happens to be called propane, by the way. This is propane. You might be using that in your barbecues. Is it balanced? We got 3 carbons here, 3 carbons there. I've got 8 hydrogens here. 4 times 2 is 8 hydrogens there. 5 times 2 is 10 oxygens. 3 times 2 is 6, plus 4 times 1 is 4. 6 plus 4 is 10. 10 equals 10. So that's a balanced chemical equation. These are the coefficients, right? You see the 5 there, the 3 there, the 4 there. You don't see anything there, so that's assumed to be a 1, right? You don't actually, it's not wrong to write the 1, it just looks weird. The chemist goes, why'd you write the 1 there? It's not wrong, but nobody writes the 1. Those give me the stoichiometric factors. So there's a whole bunch of combinations, right? I could look at this in many ways, right? I could say, now let's look at it from an atomic point of view. 1 molecule of propane reacts with 5 molecules of oxygen to give me 3 molecules of carbon dioxide and 4 molecules of water. I could look at it that way. But technically, couldn't I multiply this by 2 and it'd still be balanced? I could have 2, 10, 6, and 8. It would still be balanced, right? I could multiply everything by 10. 10, 50, 30, 40. It'd still technically be balanced, but you always want the lowest integer ratio. But it's still technically balanced. So could I actually multiply everything by 6.022 times 10 to the 23rd? Have 6.022 times 10 to the 23rd molecules of propane. 5 times 6.022 times 10 to the 23rd, or Avogadro's number. 3 times Avogadro's number. 4 times Avogadro's number. It would still technically be balanced. But isn't 6.022 times 10 to the 23rd 1 mole? Oh! So rather than using molecules and atoms to balance things, we almost always use moles to do it. So we're going to use units of moles. Very important. So this is how you're going to be reading almost every chemical equation from now on. 1 mole of propane reacts with 5 moles of diatomic oxygen, providing 3 moles of CO2 or carbon dioxide and 4 moles of water. That's an ugly looking G right there. Whoa. Now I can set up these stoichiometric ratios. Look at the many different ways I could do this. You ready? So I could say 1 mole of propane. Now, how are we going to set this up? It's a ratio, right? Reacts with 5 moles of oxygen, correct? So I could say that reacts with 5 moles of oxygen, but I can write that as a stoichiometric ratio or factor. 5 moles of oxygen. I can use that as a link in a dimensional analysis problem or Reunified Equation. So if I'm converting from moles of oxygen to moles of C3H8. So let's say I had a certain amount of oxygen. I want to go, well, how much propane reacts with it? Start with the amount of oxygen here. This allows you to cancel out moles of oxygen to get to moles of propane. And then you can go from moles to grams or whatever, right? It doesn't matter. But once you're in moles, you could get to masses and volumes if you have densities. I could flip that upside down. I could say 5 moles of oxygen is the same as 1 mole of propane. So in this scenario, if I started with propane and wanted to figure out how much oxygen reacts with it, start with the amount of protein, whatever I'm giving you, get to moles of propane, and then cancel out moles of propane to get moles of oxygen. It's just a conversion factor. That's all it is. And I could set up any ratio, right? So I could flip it up or down depending which species you're starting with, but I could go a reactant to product. I could say 5 moles of oxygen produces 3 moles of carbon dioxide. Or I could flip that upside down and go 3 moles of carbon dioxide over 5 moles of oxygen. I could say 5 moles of oxygen produces 4 moles of water. Or flip it upside down. Or I could say 3 moles of CO2 is equivalent to 4 moles of water. Any combination of any 2 species in any direction you want. So how do you know which way? Which one's in the numerator or denominator? Well, it depends what you're starting with. All that is a conversion factor, just like going kilograms to grams or anything like that. It allows you to convert one species to another with units of moles, and the numerical value is just the stoichiometric coefficient, and these are exact values. These coefficients are exact numbers. They're not measured. So these have an unlimited number of significant digits. Really cool. So let's take this concept and let's do some stoichiometrical calculations with it, like you would do if you worked in industry or government or something. Let's get a different reaction too. Here's a very typical type of stoichiometry problem you'll run into. We're just going to apply what we learned before using dimensional analysis, set up a Untitled equation, easy peasy. The only thing new is we're going to take a balanced chemical equation and find a conversion factor to go from one species to another. That's all it is. I look at an equation and go, that's a giant conversion factor to go from moles of one species to moles of any other species. Hey, so we're going to find 2 to tango and just ignore the third one here. So here's the question. What mass of product? Obviously, there's only one product, so I don't have to identify it. And it doesn't specify the units, so we could do grams, pounds, whatever we want. How much can form when 13 grams of solid indium react with excess chlorine gas? So I didn't specify the amount of chlorine, and I said there's more than enough. So the indium's going to determine how much. We'll learn about limiting reactants later. But when the indium runs out, we can't form any more of the indium-3 chloride in this scenario. This is not one where I would expect to be able to predict the product because indium is a type 2 metal in this scenario, so it can form more than one type of charge. So I gave you the identity of the products in this scenario. Here we go. And it's balanced. I balanced it for you. If you're stuck, always do a game plan, right? If you're stuck, game plan. Figure out what species and units you're starting with. So we're starting with grams of indium and we're forming product, right? So we want to get to, and it doesn't specify the units, so let's just do grams. So I want to get to grams of indium 3 chloride. That's where I want to end up with, right? I'm starting with grams of indium. So here's my start. Here's my finish, just like plotting some kind of a trip. Where are you starting, where you're going? You got to put that in your little mappy thing. I cannot relate these by grams from this. The only thing that relates them together is the moles. So this tells me 2 moles of indium will form 2 moles of that. So I got to get to moles. So I got to go grams of what I got to moles of what I got to moles of what I want to grams of what I want, right? So let's convert that to moles of indium using the atomic mass of indium. And then I can go to moles of indium 3 chloride, right? See the 2-to-2 ratio? Use the stoichiometric factor to do that. And then once I'm in moles of my product, I can go to grams using the molar mass of that, right? So grams of what you got to moles of what you got to moles of what you want to grams of what you want. Right? Say it again. Grams of what you got to moles of what you got to moles of what you want to grams of what you want. Yeah, you got it. Tongue twister. Red leather, yellow leather, red leather, yellow leather. We can do this. This is a 1, 2, 3-step problem. Easy peasy. The only thing new is this conversion. The moles of, in this case, the reactant to moles of product. We got this, man. We can do this. So let's take the starting grams of indium. So let's take our 13 grams of indium, right? I want to convert that to moles. So let's set up our conversion. So how many grams of indium are there per mole of indium? So whatever periodic table you have, right? Obviously, whoever class you're in, use theirs. Don't just Google some weird periodic table or say, well, I used this one in my last class. No. Use the one that your current coach is giving you. Whatever the coach is giving you. So all we do is look up indium. And it looks to me like that's 114.818 right there. See that? 114.818. Don't ever truncate that or make it, don't cut off any things unless your professor says you can do that. My class, we're not going to chop anything. Use the numbers that are on there. Don't chop anything off. And that allows us to cancel out grams of what we're starting with. Now I'm in moles. Once I'm in moles, so really just take whatever you're provided, convert to moles of that substance. Or however, whatever arrows you have in your quiver, whatever's in your grab bag, whatever tricks you got, get to moles of that species. Then you can go to moles of any other species. Now I don't care about the chlorine in this problem. I care about this. So I want to go from moles of indium, my reactant, to moles of the product, the indium 3 chloride. And now what I'm going to do is I'm just going to write the number in there. There's a 2 in front of the indium, and there's a 2 in front of the indium 3 chloride. Now, a lot of you are going to go, well, that's just 1. 2 divided by 2 is just 1. So I can just write 1 to 1. Mathematically, yes, but that could confuse some people. Because if you put a 1 to 1, someone like me go, that's not a 1. That's not a 1. Right? And I'd be like, what are you doing? So I want you to get in the habit, just write the number that's the coefficient from the balanced chemical equation. Don't change it. Don't simplify it. Don't alter it. Just write it in there. Yes, it happens to be a 2-to-2 ratio, which turns out to be 1. Yay, okay, so that's an easy thing to do in your calculator, but please don't alter it. That can confuse some people. Here we go. So moles of the species I'm starting with cancel out. So check, I just did this one here. That was step 1. Check. Step 2, that's the only thing new in this whole chapter right here. That ratio, not too tough, right? Everything else we did gram to mole conversions earlier on. We did molar masses earlier on, nothing new there. So let's do our last step here. And we're going to go from moles of indium 3 chloride to grams of indium 3 chloride. We need the molar mass of this puppy. And molar mass is always for 1. Doesn't matter what that number is. Molar mass is defined as the grams per 1 mole. Doesn't matter how many moles you have, right? So we got 1 indium and 3 chlorines. So let's take chlorine, which is 35.4527. Multiply that by 3. That's good to 4 decimal places. Add your indium. 114.818. That's good to 3 decimal places. So we're limited by decimal places. It's effectively an addition problem. So we're going to be good to 3 decimal places. So I got 221.1761. So 221.176. And I'm going to put a vertical dash line because the Indian limits me to 3 decimal places. Right? And then I get a 10 after that. So 221.17610, good to 3 decimal places. Molar masses are rarely going to limit your significant digits. So now moles of the indium 3 chloride cancel out, and I'm left with grams. Didn't specify the mass, right? What units of mass. So just leave it in grams. Why convert that? I guess you could convert that to pounds if you wanted to, but what a waste of your time on an exam, right? Let's just leave it as grams. So I have 2 significant figures here, correct? 6 significant digits in the atomic mass. This is exact. 6 significant digits in the molar mass here. So I'm limited to the 2 sig figs right there. See that? Since it's all in any unit line equation or dimensional analysis, it's all multiplication division. So you're limited by sig figs. But here in the molar mass, you're limiting by decimal places to do that. You don't have to show me your calculations to get the molar mass, right? So let's punch this out. Take 13 times 1 divided by 114.818 times 2 divided by 2. You can do that in your head. Times 221.17610 divided by 1. Pop it all out on your calculator. And we get it to 2 significant digits. So I get 25. There's my 2 significant digits, so I'm going to put my vertical dash line, 0.04 grams of indium 3 chloride. And that's closer to 25 than to 26. So we're going to round this to 25 grams of indium 3 chloride. So show me the intermediate non-rounded value, units, and substance. So we're in a situation now, we have to identify what substance we're talking about. So give me the unit and the substance. So 25 grams. This is a great predictive ability. 13 grams of this can theoretically produce 25 grams of that. So we call that the theoretical maximum yield. Theoretical, because it's theoretical. Theoretical, because we didn't actually do this in a laboratory. I bet you if we did this in a lab, we wouldn't get 25.04 grams. I guarantee it. So that's the theoretical maximum yield. You don't ever have to write that. That's just what we call that in the chemistry world. What you determine from a stoichiometrical calculation is the theoretical maximum yield. If I have this much product, this much reactant, that's how much product I should get in a perfect world if every atom reacts. That term will come back to haunt us later. Let's do another example. Let's see how you do on this one, my friends. A little bit harder. I didn't give you the balanced chemical equation on this puppy. How are we going to do it? What mass of lithium solid is required to completely react with 26.5 milliliters of liquid bromine? And the density of the liquid bromine is provided as 3.119 grams per milliliter. Again, you can do grams over milliliters or grams times milliliters to the -1. Same thing. So no balanced equation, but we need it to get the mole-to-mole ratio between the lithium and the bromine and the 2 reactants. We don't even care what the product is in this scenario, but we need to identify it to figure out what the stoichiometric ratios are. So let's always start with a balanced chemical equation if you're not provided one. So here's my solid lithium. Remember, bromine's one of those diatomics, okay? And mercury, right? The only liquids at room temperature. Now, this is a synthesis, so lithium's an alkali metal, so that'll form a +1 cation. Bromine, that's a halogen, that forms a halide, which is a -1. So lithium's a +1, bromide's a -1. They'll go together in a 1-to-1 ratio. So that'll give me lithium bromide. Now remember, salts, cation plus anion, in this class at room temperature are always going to be solids for this class. So we got lithium bromide solid. Lithium 1 and 1, bromine 2, bromine 1. So I need a 2 here to balance my bromines. So I got 1 lithium, 2 lithiums. Uh-oh, it screwed up my lithiums. There we go. So 2 moles of lithium react with 1 mole of bromine to give me 2 moles of lithium bromide. So see the 2-to-1 ratio there? I'm going to need that to convert from the lithium to the bromine or the bromine to the lithium, depending which way I go. I'm not even worried about this. So let's look at what we're starting with. We're solving for this, right? We're starting with this. So we're going from the bromine to the lithium. And we're given 26.5 milliliters of this with that density. So I'm going to start with the milliliters of bromine, use the density to convert that to mass, go to moles. Remember, no matter what you provided, get to moles, get to moles, get to moles. And then 1 mole of bromine requires 2 moles of lithium to react with it. And once we get moles of lithium, we can get grams. If you don't have the faintest idea what I just said, let's do a game plan. You ready? We're starting with the bromium, solving for lithium. Okay, so start with bromine, milliliters. So we're taking milliliters of bromine, and we want to get to, it doesn't say mass again, so let's just do grams. We want to get to grams of lithium. So we got to connect those. That's our journey. Type it into your maps program, bloop, and off we go. I got to get to moles. Everybody agree I got to get to moles. So I've got to get to moles of bromine so I can get to moles of lithium. Would you all agree that I can get from moles of lithium to grams of lithium using the atomic mass of lithium? Oh, easy. So all I got to do is get from milliliters to moles, but I can't do volume to moles. I can go mass to moles, so I need to get to the mass of bromine first, which volume to mass requires density. Yay, right? Grams and milliliters. See that? So milliliters here. So if I wasn't in milliliters, I'd have to convert to units of milliliters to go from milliliters to grams using density. So I can get from milliliters of bromine to grams of bromine using density. Right, density there, grams of bromine to moles of bromine, get the molar mass of bromine because it's diatomic, bromine plus bromine. I can go from moles of bromine to moles of lithium, see the 1-to-2 ratio, that's my stoichiometric factor, and then moles of lithium to grams of lithium there. The only thing new is that conversion factor right there. Everything else you've done, you've used density to convert volume to mass, mass to volume, a lot. I love doing that. We've done atomic mass conversions. We've done molar mass conversions. So the only thing new is that stoichiometric factor. That's it. It's not too tough. Stoichiometry is exceedingly logical, right? Let's do it, my friends. So let's take the 26.5 milliliters of bromine. That's what we're starting with. I got to get from milliliters to grams. Let's use the density that was provided. That's not an exact value, by the way. So there are 3.119 grams of bromine. Now, remember, you've got to put the species there. You just can't put grams per milliliter. So if you don't put bromine there and you just put 26.5 milliliters, are you talking about milliliters of bromine, milliliters of this, that? We got 3 different species on the playing field here. You need to specify, if you say moles or grams or milliliters, which species you're talking about. Right? And I know a lot of you can do that in your head, but the person reading your paper maybe can't do that. And if you lose track of what species you're on, then you start applying the density to the wrong substance. I see it all the time. So just take that extra half a second to write what species you've got. Okay? So milliliters bromine cancels out. Bye-bye. Now I can go from grams of bromine to moles of bromine. Right? So grams of bromine go on the bottom. 1 mole of bromine goes on the top. Woo, that's a big R. So let's take bromine. Now it's diatomic, so I got to take this number. Where's bromine? 79.904. Do you see the 79.904 for the bromine? So I'm going to take 79.904 plus 79.904, or times 2. It's good to 3 decimal places. I had a pen once. So let's take 79.904. And that gives me 159.808. So 159.808. Good to 3 decimal places because you're adding 2 bromines together. That allows me to cancel grams of bromine. Yay! Now I can do the stoichiometry. I'm starting with moles of bromine. I'm trying to solve for how much lithium I need to completely react with that. Very common in industry. I've got this much of this species. How much of the other one do I need? I need to go purchase this, and figure out my overhead and all that. So there's a 1 in front of the bromine and a 2 in front of the lithium. Those are exact numbers. So I got 3 sig figs here, 4 there, 6 there. That's exact. Now I can do my last one, moles of lithium. So for every mole of lithium, how many grams of lithium? And I'm doing a super squish factor here because I've run out of board space. You don't have that limitation. So let's look up lithium. That's an alkaline metal. You see the 6.941 there, my friends? 6.941. 6.941 grams of lithium per mole. Let's see, we got moles of bromine cancel, moles of lithium cancel. The only thing left is grams of lithium. Hey, just leave it there, right? I didn't specify the units, so let's just leave it as grams. 4 sig figs exact, 6 sig figs 4, so I'm limited to 3 significant digits when I do this calculation. So pop this out, I get 7.17, vertical dash line, because there's our 3 significant digits, 7.1798 grams of lithium. That's closer to 7.18 than it is to 7.17. So that's bigger than 50, right? So it's going to round up to 7.18 grams of lithium. Very common. Expect something almost exactly like this on your exam. You good? I could go on and on and on and on, relating any 2 species that I want. I think you guys got stoichiometry down. Let's end this video.